Hi everybody, I hope you're doing okay. This is a continuation of Friday's lesson. So Friday I introduced the concept of LeChatelier's principle, which states that if you have a system that's at equilibrium, where the rates of the forward and reverse reactions are equal, and then you disturb it in some way, the reactions will respond in order to reestablish that balance. So the other day we looked at concentration, a change in concentration, how that affects equilibrium, and a change in temperature. So if I increase the concentration of a particular substance, increase concentration, the reaction, the direction will shift away from that increase, and the substances that are in the system will either increase or decrease in response to that. For temperature, you have to look at where the heat is in the reaction. If the heat is on the left, that's where you're going to say the temperature increases. If the heat is on the right, that's where you're going to say the temperature increases. That's not actually what happens, though. You can't just increase the temperature of one thing in a closed system. Like if you heat it up, everything gets heated up. So the real explanation is increasing temperature favors an endothermic direction, decreasing would favor exo. But to help you remember it, we use like this little acronym. Today we're going to talk about two other factors. This one is a change in pressure. Okay, so if I have a system of gases, and you must have gases in your system, it doesn't have to be all gases. It'll give you the phases, in parentheses after the formulas. The system doesn't have to only contain gases, but it must contain some gases, and that's what will be affected by changes in pressure, because other phases of matter aren't affected by pressure because you can't compress them. When you increase the pressure of a system, you're basically increasing the concentration, because when you increase the pressure, that means you're decreasing the volume. So that's that, when we talked about gas laws and they were, the container with a movable piston where this plunger could move up and down. If I wanted to increase the pressure, I could push down on the plunger, which would decrease the volume. That would make them collide more frequently. It's not speeding them up. Okay, so something to keep in mind again is the only time you want to mention a change in speed is when you're talking about a temperature change. Otherwise, you're not making them move faster. You're just making them collide more often because of their proximity to each other. So the rule of the pressure change is that if you add pressure to a system, the reaction will shift to the side that has the least number of gas molecules. Now, how do I know? By looking at the equation how many molecules are present? You look at the coefficients. So you look at the total coefficients of gases. So you count your coefficients and you shift to the side that has less for the total number of coefficients. So here's an example. This is a synthesis of ammonia. This is called the Haber process. And it's reversible, so I could take a nitrogen and hydrogen and react it to make ammonia just as quickly as the ammonia will decompose into nitrogen and hydrogen, as long as it's in a closed system. So I have this sort of thing going on here. So if I'm just going to count based on the numbers that are in my equation. So here's nitrogen molecule. There's 1 mole of nitrogen. There's 3 moles of hydrogen. So here's a hydrogen. Hydrogen. All right, I'm doing these in groups of 2. And then I have 2 NH3s. So here's NHHH. NHHH. Okay, so if I add pressure to the system, that means I'm pushing down on the plunger to decrease its volume. So let's say I do this. I'm not changing the number of molecules, right? I'm just going to put them closer to one another. I'm not changing how fast they're moving. So you can see, obviously, there's less space in between these particles. Now, if I add pressure to the system, I cannot put like a little arrow over any particular substance like I could with concentration changes, or like I could put an arrow over the heat with the temperature change. Because when you add pressure to the system, you're putting pressure on everything that's in the system. Now, so all you have to do if you add pressure, the way you're going to remember this is PIL. If the pressure increases, you shift to the side that has less, some people think I say left here, but no, less moles of gas. So you count your coefficients. So on the left-hand side of the reaction, remember this is a 1 here, there's a total of 4 moles of gas. And on the right side of the reaction, there's a total of 2 moles of gas. So if I add pressure to the system, it's going to shift to the side with less moles of gas, so the forward reaction is favored. Now let's see what happens to the substances when I shift it forward. So the forward reaction is the reaction between nitrogen and hydrogen to make ammonia. So that means that the concentration of the ammonia will respond by increasing, and the concentrations of the nitrogen and the hydrogen will respond by decreasing, because they're getting used up in order to make more of the ammonia, okay? If I decrease the pressure, everything would be the opposite. So in these videos, I'm introducing these concepts, and then I'm going to work through some examples with you in practice problems. So here's another one. These are all gases, so we know that a pressure change will have an impact here. So for this, if pressure is added to the system, keeping in mind this PIL, we count the coefficients. So on the left-hand side, I have a total of 2 moles of gases. On the right-hand side, I also have a total of 2 moles of gases. If you have the same number of moles of gas on each side of your equation, there will be no effect. It will not stress out the system if you increase the pressure. So your reaction rates of your forward and reverse reactions would remain equal. You wouldn't have one reaction favored over the other. So what would happen to the concentrations? They would remain the same. Okay, so this is really the only factor where you could, well, no, the next one is too, where you could have no effect on substances because there's equal number of moles of gas on each side. This factor, adding a catalyst. So for a catalyst, in terms of a potential energy diagram, which we've already looked at, a catalyst will affect the activation energy of the forward reaction. It used to be this tall blue arrow, and then with a catalyst, it's the shorter one. It will also affect the activation energy of the reverse reaction, which was this taller red arrow versus the shorter red arrow. So a catalyst will speed up a forward and reverse reaction equally. It does not favor one process over another. So therefore, adding a catalyst will give you no change. It doesn't stress out the system. It speeds up both reactions equally. So it's kind of a trick question. What effect would the addition of a catalyst have on the concentrations of each of the substances? It would have no effect because it's not disrupting. This is actually a poor example. I could just do that. But yeah, you would have no effect on the concentrations. That's it for a catalyst. There's no mnemonic there. It just doesn't affect anything. Well, it speeds both of them up. It doesn't favor one over the other. The last one here is called the common ion effect. So the common ion effect is when you're adding a substance to a reaction and that substance isn't in the existing equation, but part of it is. So it's treated like a concentration problem where we have that CIA. So let me show you. So this would be an equation for the dissolving of sodium chloride. When sodium chloride dissolves, the ions separate from one another. So if I asked you, well, if I added more sodium ions, which way would the reaction shift? You would think, okay, if I'm adding something, that's a CIA problem. If I added sodium ions, the reaction would shift to the left. And if it shifts to the left, the direction that the arrow is pointing in, that's the substances that are going to increase as a result. And anything that's left over, like this chloride, is going to decrease because it's reacting with the sodium to form sodium chloride. So this would go up, this would go down. Now, if I asked you this particular question, I have the same starting reaction. So this would be a saturated solution. A saturated solution is at equilibrium. So the rate of the sodium chloride dissolving into sodium ions and chloride ions is equal to the rate of the sodium and chloride ions crystallizing out. That's what equilibrium in a solution means. If I added magnesium chloride or potassium chloride or something to the system, and you're like, wait, that's not in my reaction already, you look for the ion that is in the system already. So in this case, if I, for example, added potassium chloride, what am I really doing? I'm really adding chloride ions. Okay, so if I added chloride ions, and I keep in mind my CIA, if I add chloride ions, my reaction will shift away from where that was added, so it'll shift to the left. The direction in which the arrow is pointing, the substances that are in that direction are going to go up. Okay, so that means this goes up. What would happen to the amount of sodium? Well, if it's going to the left, that means the sodium is starting to get used up, so it's going to drop. This would increase because it's added. So that's it for common ion effect. I know this is a lot. I really wish we could work on this together. But I'm gonna post a couple of other videos to help you out. Hopefully I can find some graphs or particle diagrams and things to help you with. But we're gonna work on this concept for a couple of days of equilibrium. Okay, have a good one.